Hello, it's Keith here, and this is lesson 81 of the platform-specific series of my Z80 programming tutorials. Now, today we're going to be looking at the Sam Coupe, and the example we're looking at this time is going to be a 16-color tile map using my Mintile system. Mintile is a multi-platform piece of code. Most of the code is multi-platform, but there's a small platform-specific module that actually draws the graphics to the screen, because that's very different on the different systems. Now we're looking at the 16 color version today, and you can see it running here. It allows us to have a simple tile map, it can scroll, and it can do X flip of the simulated sprites. I refer to them as simulated sprites because they're actually miniature tile maps drawn at alternate positions rather than filling the full screen. The reason for this is that means we can use the same code for the tile maps as the sprites, and it also has some weird advantages with regards to because we're making it out of 8x8 blocks, we can reuse parts of the sprites and save a little bit of memory in some cases. But as I say, the main reason that choice was made is to actually reduce the coding. Now, the 16 color version that you can see today is very good. It works fine. Now, one thing that I have decided to do though is I've also made a 4 color version. The reason for that is partially to save memory. If we use 4 color patterns and convert them to 16 colors, then we can save some pattern data, and that makes the program smaller, less bank switching. Also, the game was originally designed for 4 colors, so in some cases it's beneficial. This was used originally for a game called Chibi Fighter. It was a parody of Street Fighter. Now, so we're going to be looking at the 16 color version today. So as always, you can go to my website and download the source code and the build scripts, and as I say, you're welcome to use them any way you can. So this is the file we're looking at today. So let's take a look at the code. Now, the first thing to notice is we're actually loading our program in we load in at the memory address 8000, but we actually then copy it to memory address 100 in hexadecimal here. So we're actually running from the low memory area. Now, the reason we're running from that low memory area is because we're going to bank switch in the VRAM into the high memory area, and we also want the memory address 0038 to be available for us to install an interrupt handler. So we've got a dummy interrupt handler here. We've not actually got a real practical one, but if we wanted to play music, we would use that to do so. So that's what we're doing here. We're basically bank switching in the memory that the program was loaded into originally at 8000, and we're bank switching it into the low memory area so we can then run it, and we're then jumping to the new memory address, which is 100. All of this is relative code, so this will, well, actually there's no jumps or calls or anything anyway, so this will run from any memory address, and once we jump to the fixed memory address of 100, that will actually be paged into the correct address. Got a dummy interrupt handler here, we've got a palette loading routine here, and we've got the code to set up the timer. Now, we're not going to look at the code that relates to Mintile itself. There's a whole tutorial series on that. We're also not going to have a look at this just yet. We'll come back to that later. So the thing we're going to look at today is the code that actually handles the graphics routines. Now, the first thing we have is a get screen pods function here, and this is a good time to discuss the screen memory layout of the Sam Coupe and why it's very convenient for us. Now, on all of the systems, we're working in what I refer to as logical units. The rule is that basically one logical unit is 2 pixels or 2 lines if we're going vertically. The reason for this is that the systems I tend to work on have a screen width of around 256 and a height of 192, and we want to work in a single byte coordinate because we're on 8-bit systems, that's faster. But the problem is that we need some areas to be off screen so we can have sprites come into the screen and sprites go out of the screen. So if we just use a single byte, that wouldn't give us any leeway to do so. But by working as one logical unit equals 2 pixels, that makes our screen 128 logical units wide. We've got an off-area screen at the edges there, so that's what I do. Now, that works quite conveniently for this system because basically 1 byte contains 2 pixels, so one logical unit is effectively 1 screen byte horizontally, and vertically it actually worked quite well as well because there's 128 bytes on a line, so 2 lines are 256 bytes, and so basically all we're doing here is we are taking the Y position in logical units, oring in the screen base at 8000, that's the start of the screen memory, and then that is the top byte of the destination RAM address, and then we're loading the X coordinate in logical units into the L byte, and that's the HL destination. That is only used for the sprites. You can see those little sprites that will move around the screen. When it comes to actually drawing the entire screen, we just use a predefined screen base here. There's a symbol there defining the screen base, and that's all we use for cases where we're filling the entire screen. So that is just used for drawing the sprites. Now, when it comes to drawing a tile map, whether it's the entire screen or just a little sprite, what we do is we split it up into strips. The main multi-platform routines will call the do strip routine, which will draw each strip of the line of the sprite or the tile map 1 line at a time. So it goes across like that, moves down, goes across like that, and moves down. And so that's what we're going to be looking at here. Now this version actually uses stack misuse. Now that has a bit of a disadvantage because that means it could cause us some problems with our music, but it is going to be faster, especially for 16 colors, because it's quite a lot of data we're going to be pushing around. So what we're going to do is we're going to transfer the data from the pattern that's specified by the tile map, and we're going to move it to the screen. But we're going to do some tricky stuff first, because basically we're going to take advantage of the screen memory layout and to allow us to quickly move down a line. When we are drawing our tile, we're going to start from a position that's either going to have the bottom byte as from 0 to 127 or 128 to 255, depending on if we're on an odd or even line. So what we're doing here is we're basically calculating in advance those two possible low bytes of the HL address for each line of the tile, and we're loading them into the B register and the C register for later. You'll notice we're switching to the shadow registers after that to get the actual tile number we want to show, and in those shadow registers the BC register points to the tile map. Now the tile map itself has a thing where if the tile number is 0, then that's a tile not to be drawn. In the case of a sprite, that means a transparent area, and in the case of the tile map is actually a cache of changes, and so if the tile has been changed to a 0, that means it's not been changed since the last draw and doesn't need drawing again this time. So that's why skipping here if the byte loaded in is a 0. Otherwise, what we're going to do is we are going to load that into H, and then we're actually zeroing the byte in the tile map. However, if we're drawing the sprite, we would want that to be left the same, and so we've got self-modifying code, and we can change that to a no-op via that self-modifying code. What we're then doing is we're then shifting H and the L part, which is currently in the accumulator, and we're effectively multiplying the tile number by 32. It's an 8x8 pattern, and basically there's 2 pixels per byte, and so that's 32 bytes per pattern. So by doing this, we're calculating the offset for the pattern that we want to show to the screen. We're then adding the DE pair, which is the base of the pattern data. I do have some pattern data lurking around somewhere here. Here it is, here's the pattern data. So this has all been outputted with the Sprite editor, and you can see it's actually the same format in some cases as the MSX version, because that's also a 16 color system in the same format. Okay, so we've now got our tile source, and we're then moving that to the stack pointer. So we're using stack misuse here. That's why we backed up the true stack pointer up here. Now what we're going to do is we're going to pop 2 bytes off the stack. That's 2 bytes worth of screen data, and we're transferring them with 2 load commands, and we're only incrementing the L byte of the HLVRAM destination, because we know that it'll go from 0 to 127 or 128 to 255 on a single line. So we don't need to increment H, that saves us some speed. Now once we've done a pair of bytes, we're then loading the L part with the value in the C register, which is the pre-calculated value for the next line here. So that's the odd line calculation, and this actually works very well because the coordinates for our sprite's position are in pairs of lines. We know it's going to start on an even line, and the next line afterwards will be odd. If we had a coordinate system that worked in single lines, then this wouldn't work. We'd have to either use more complex calculations or have 2 versions of this code. So that is doing the first line. We're then doing the exact same thing here, only this time we're loading L from the B register and incrementing H, because we now need to move down another line, and the H part also needs to be updated. We're then proceeding to do that. Each of these is 1 line, so that's 2 lines, that's 4 lines, that's 6 lines, and that's 8 lines. So we've transferred all of our tile data to the screen. Now what we're doing here is we're moving back up to the top of the tile. We're then moving across the tile map. So we've drawn the tile down, we're then jumping back up and moving across to do the next tile. So it does 1 tile at a time, this code. And then we're decreasing IYL, which is the tile count. So we're repeating until the entire strip has been drawn, either the full width of the screen or the full width of the sprite. And then we're restoring the stack pointer. That will be changed to the correct stack pointer by self-modifying code, and then we return. The empty tile code simply skips over the current tile and moves the destination VRAM to the next position, and then returns as well. So that's how that works. Now that's for the regular sprites, but we do have the option of X-flipping the sprites. You can see here, if I press the enter key, I'll press it a bit more slowly there we go, the sprite will flip. Now what we could do is we could have a second set of pattern data to do that. That's not going to be very efficient though, so we haven't done that. What we've got is we've got a lookup table of 256 bytes, and what we're going to do is each entry in that table is going to contain the flipped equivalent of the byte we want to convert. So we will use that to quickly convert the data. Now it's aligned on an 8-bit boundary, and that means it will have a bottom byte that starts at 00, and it will go all the way to a bottom byte of 255. Now what we're going to do is we're going to treat that bottom byte of the memory address as the source data that we want to flip. And then we're going to calculate the flipped equivalent and write it to that memory address. And what that means is if we load BC, which is what we'll use, if we load a pair of registers with the address of the lookup table and then load the low part with the value we want to convert, when we read back from the resulting address, the result will actually be the flipped equivalent of the byte that we put into the low part of the address. So we're loading HL with flip-a-lot here. We're then loading the accumulator with the L part, the low part of that, and that's the byte we want to flip. We're then flipping the 2 pixels, which is simply 4 rotate commands, which just basically swaps the bits of the 2 pixels around within the byte. And we're then writing it back to the HL destination. We're incrementing L, and we're repeating when L becomes 0, because then it will have gone over the 0 to 255 range and we'll have done the entire lookup table. Okay, so that's how we create our lookup table for XFlip. Now, what we've actually got then is we've got an alternate version of our code, which I currently can't find. Here it is. So this time, we used BC last time for speeding up the moving down a line calculations. However, this time we're using them for the lookup table. So we're loading the address of the lookup table into BC here. Okay. Firstly, what we do is we calculate the address of the pattern data in the same way. And then what we do next is, once again, we read in the pattern data from the stack. And then this time, though, rather than writing it to the screen, we actually load the C part of the BC pair with the byte we want to convert. Remember, BC was loaded with the lookup table. Now what we do next is we read in a byte from BC into the accumulator and then write that to the screen, because when we read in from BC, after changing C to the byte we want to flip, we read back the flipped equivalent, and so that has XFlipped this byte. We then do another byte for D, the pair from the pair we read in, and we then do a second byte. That has now done the entire tile, and we need to move down a line. Now this time we don't have enough spare registers to do the speed up we did before, so this time we've got a calculated version here. So we're moving down a line here, we're then doing the same, and we're moving down a line and incrementing H. Now because there's so much code here, I did decide to use a loop this time. I could have unwrapped the loop and just had tons and tons of copies of this. It felt excessive, so I haven't done that in this case, and I've got a loop here in L in the shadow registers here, so I'm loading L with 4 there. And so here we're decrementing that loop counter and we're repeating. So that's how we are X-flipping the data. Now if you wanted to Y-flip the data, which I'm doing in a successor to this, but what all you would do is basically either start reading the pattern data in reverse or writing the pattern data in the screen in reverse. And if you want to do both, you would use the lookup table from the X-flip and the Y-flip. Now I am doing both in a tutorial series which I'm currently working on, which is an extended version of this. This is called Mintile. The successor is called Maxtile. It does X-flip, Y-flip. It does double height scaling, solid fills that are faster and things like that. So I've got a lot of things that I'm doing with that, and that will come down later in the pipe, but it's still in early development at the moment. So as I say, you're welcome to go to my website and download this, and if you can make any use parts of it, go ahead and do so, or maybe you'll just get some inspiration, maybe it'll help you understand how to use lookup tables for fast conversion of data. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.